Hello, everyone. Welcome to this new webinar. I'm Marie here with Karim Azoum. We are from the French Competence Center, it's part of the EuroCC project, and with Pierre Aubert from the lab in Annecy. Together, we organize the Grey Scott Thursdays and the Grey Scott School. So welcome to this new session. As always, those weekly webinars explore the key topics from the Grey Scott School curriculum and progressively prepare you for the summer school this summer. So a quick update before we begin. Registrations for the Grey Scott School 2026 are still open. And we're very happy to see new satellite sites opening across several European countries too. So the network keeps growing every week. There are spots available in Annecy to spend the full 2 weeks with the teacher. Please register and come with us. You can also attend from the satellite sites. You have the full list on our website. I will share the links later. And you can also attend online. For Annecy, just for you to know, if accommodation is a concern, don't worry. We have some housing options and plans to help the participants find a place to stay. So you just need to connect with us and you'll be able to have the great opportunity to spend the full 2 weeks with the teacher on site. It's a very great way to attend the Grey Scott School and to benefit from this incredible training.
Could a simple chemical reaction teach you how to unlock peak performance on today's supercomputers? Welcome to the Grey Scott School 2026, a free, advanced summer school on high-performance computing. Designed for professionals from industry, public sector organizations, and academia. From June 22nd to July 3rd, 2026, join us in Annecy, France at LAP, at one of our satellite sites across Europe, or online via live streaming. All courses are taught in English. You can pick the courses most relevant to you or dive into the full 2-week program. You'll learn the practical behavior of modern hardware and how to write performance-optimized portable code. Week 1 focuses on CPUs, Week 2 on GPUs, covering architecture, bottlenecks, parallelism, memory, and performance analysis. All learning is built around a single challenge, simulating the Grey Scott reaction. Simple to start, yet complex enough to stress compilers and expose performance limits. You'll explore modern tools, languages, and libraries such as C++ 17 and 20, CUDA, Fortran, Python, OpenMP, TBB, Kakos, PyTorch, and more. The school provides ready-to-use container environments for smooth hands-on sessions. Expert instructors from CNRS and CEA guide you with live Q&A and community support on Discord. Satellite sites let you learn together locally without traveling. Want to host one? It's easy with our turnkey setup, sharing the school with your colleagues and ecosystem. You'll leave not only with hands-on HPC skills, but also an official certificate of participation. And you know what? You can start early with 18 Grey Scott Thursdays webinars, weekly from January 29th to June 11th, introducing summer school concepts and new topics. Whether you're an industry professional, engineer, researcher, or student, if you have programming experience and want to push your skills further, this program is for you. Register now at cc-fr.eu and start learning today. Grey Scott School 2026, Europe's leading HPC summer school.
So everything is free, of course, open to everyone. If you find those webinars useful, please spread the word around you. Talk about the summer school too. We'll be very happy to have you with us. Today's webinar will focus on Python and GPUs to be presented by Alice Faure and Jean-Marc Colley. A great session for anyone interested in accelerating scientific applications with modern Python tools. So now I'll give the floor to Pierre Aubert, the creator of the school, who will present them better than me. Pierre, the floor is yours.
Okay, thank you, Mary, for the nice presentation. I will add a little thing also to what you just said, Mary. If you are curious and you want to attend the school, or you don't really know if it's for you or not, you can have a look to the short presentation of the school, of the feedback of the attendees last year. So there is some shorts in EuroCCFR YouTube channel. If you want to know in 40, 60 seconds what's going on one or what topic, you can have some feedback directly, just to, if you are afraid of the amount of work that we present or some stuff like this. So don't hesitate to have a look. It's really nice. It's really nice to look at it. Really simple to get. So without further ado, let's present also Alice and Jean-Marc. So you know them, of course, from last week, but I will present them again. So Alice is working at LUPM, so Laboratory of Montpellier of particle physics. So in basically on gyroscope telescope array simulation, so particularly on the Corsica 8 program, so particle cascade simulation. So if you get a particle entering the atmosphere, you get a particle cascade, and it's really difficult to simulate that, particularly on GPU and on CPU. And Jean-Marc is working in ZIF experiments, so the Weakly Transient Facility experiments, so large field astronomy data processing. So it's a radio telescope like LOFA or SCARA. And without further ado, we'll have a look to Python for GPU. And if you have some question, please use the chat and we will answer all the questions at the end of the session as always. So Alice and Jean-Marc, it's up to you.
Thank you, Pierre. So we're going to start with a brief introduction. So what we are going to present in this webinar are a few libraries to compute on GPU with Python. We chose three to present on this webinar, the three that are in pink in this slide. So QPyNumeric, JAX, and QPy. Unfortunately, we cannot present PyTorch today. We just have a brief slide on it at the end of the webinar. So we try to focus on high-level libraries like QPyNumeric or JAX. On these libraries, there are a few efforts required to change from the CPU to the GPU. So it's a bit, it can be easier to use. We also present QPy, which is, we sort it in an intermediate level. For us, it means that porting your code with QPy is less easy than the other libraries, but it's still very efficient. And there are also some low-level libraries, like more specific to the architecture, more CUDA-style libraries, like PyCUDA or Numba for GPU. We are not going to talk about them today. We're just going to present Numba for GPU briefly at the end of the webinar. Okay, so let's start this presentation by giving some general advice on profiling and benchmarking when you want to do it on a GPU. So as you may know, if you want to check your GPU use, you can use the NVTop directive instead of HTOP for CPU. When you want to profile your program, you can use, if you have an NVIDIA GPU, you can use Insight. If you have AMD, you can use RockProf. There are also some Python profilers that I think Jean-Marc is going to talk about later. One thing to keep in mind when you want to benchmark your code, however, is that execution on the GPU is asynchronous. So you cannot use the tools for CPU that we recommended in the last webinar. So for example, the timeit module, which times some functions or some parts of your code. You cannot use it on a GPU because it will give you a timing that is wrong. And so if you want to benchmark your code, you need to use the dedicated functions of each library that we're going to present. So here I put the example of the CuPy-dog. For CuPy, if you want to benchmark your code, you have to use the CuPy dot profiler benchmark function. And for CuPy numeric, it's the same. You have to import legate dot timing, and it's the time function that you have to use. Okay, so this was a brief introduction on how you can time things in your program. I'm going to start this webinar with the first library that I talked about, which is CuPy numeric. So it's an NVIDIA library to compute on GPU, and it's based on legate. So here is a brief presentation of legate. So you may know it. It's an NVIDIA project that is aimed at democratizing distributed and heterogeneous computing on CPU or GPU. So the goal is to be able to compute on single CPU, single GPU, multi-GPUs, multi-nodes, multi-GPUs, etc. So the thing is, with legate, parallelization is implicit. So you don't have to worry about it when you write your code. So yeah, legate is a basic block of CuPy numeric. And let's check on the next slide what exactly is CuPy numeric. So it's a library that is a NumPy drop-in replacement. So instead of importing NumPy, you import CuPy numeric and you use it as you would use NumPy. The aim is for it to be really easy to use. And so the point is, when you use it, you can have the same code that run on CPU or on multi-node, multi-GPU clusters. So here is an example of the proof of concept that they made for CuPy numeric. It's a weak scaling example in which when you increase the number of GPUs that you use with CuPy numeric, you can process a bigger set of data. So this is the goal of CuPy numeric, is to be able to switch from CPU to GPU or multi-GPUs in order to process more things. How does it work? And first of all, maybe on the next slide, I will give a brief history of CuPy numeric because it can be a bit messy if you follow the project from its beginning. So first of all, it's a library that is still in its beta phase. And the first beta release was in 2023, so it's very recent. This is why it's not profusely used in the Python community, I would say. At first, it was called legate numpy, then it was called qnumeric, and now it's called CuPy numeric. So sometimes you might see the words qnumeric when you look at things about CuPy numeric online. So the first beta release of CuPy numeric was 2 years ago. So it's a very recent project. Now, how do we install it and how do we use it? So we can install it via conda or pip, so it's really easy. And as I said, it's a NumPy drop-in replacement. So that means that to use it, you just have to import it as NumPy. So you type import CuPy numeric as NP, and then all your NPy dot etc. functions are going to use the CuPy numeric equivalent. To execute it, this is a bit different than what you may know. It's better to use the legate driver, because this gives you options to specify on which architecture you want to compute. So here on this example, you choose to compute on 2 GPUs and 2 CPUs, and you also specify the frame buffer memory here of 2 GB. Okay, so a brief thing to keep in mind is that just like the CPU optimization libraries that we presented in the last webinar last week, the use of CuPy numeric will be all the more effective if the code uses NumPy arrays and functions. So we'll describe a bit how does it work, because the thing is, you're not supposed to make any changes to your code. So how does it work to distribute your computation to the CPUs or the GPUs? It works on implicit parallelization. So there are 2 kinds of parallelization that are made by CuPy numeric, and well, it's made by legate because CuPy numeric is based on legate. So the first one is parallelization on data. So the library CuPyNumeric will partition the data across the CPUs or the GPUs you want to compute on. And then it will also do a parallelization on tasks. So it will produce a task graph, and it will handle the execution of the different tasks and their dependencies asynchronously. So you can perform independent operations simultaneously. And so you can hide communication latency between the CPU and the GPU, for example, behind a useful computation that is independent to communication. So for example, you have here an example of a directed acyclic graph that is produced by CuPyNumeric, in which you have the computation in green and the data transfers in gray. And you can actually do these tasks, the computation and the data transfers, simultaneously because they are independent. And so it can hide the latency of the communication tasks. Okay, let's check out an example that they give in the CuPyNumeric doc to see how it works. So this is a stencil example that they provide. Last year I tried it, this year I tried it. 2 years ago it didn't work, but from last year it works. So it's actually an example in which you apply a Jacobi stencil on a grid to mimic the diffusion of heat in a medium. So on this example, you can see we import CuPyNumeric as NP. We import the time function from the legate.timing module. So this is to benchmark our program to see how long it takes to execute. So we make a grid of 100 times 100 elements. And we run a stencil on it, and we do this 1,000 times. So on the next slide, you can see how we execute this program. So if you want to execute on the architecture you are on, the thing is Legate will automatically execute on the everything that you have available. So if you are, for example, on a GPU and you want to test only on the CPU to see if you have some differences, you have to specify GPUs 0 so that you don't use the GPU that you have if you want to test on the CPU. So this is a subtlety. But yeah, if you are just on a CPU, a regular CPU, you can just put CPUs 1 and then it will run on your CPU. So to run on your GPU, you just have to specify GPU 1. And in my case, but maybe it's just dependent from my configuration, I always have to put the frame buffer memory option. If I don't put it, it will try to allocate the higher memory than what I have. Okay, so this you can see that you can run the exact same code on CPU or on GPU just by changing the options that you give to the Legate driver. So these are results from last year, the timing results. So on the GPU, it was only 3 times faster than on the CPU, which is not good. But I have to say I used a very quite old GPU because it was a Quadro, I think, with a small memory, and also it was last year. I think this year it's a bit different in terms of performance, but we're going to see it in the Gray Scott School in July. Okay, maybe some specifics that I discovered when I use CuPyNumeric. If you try to call a function that doesn't have any equivalent in CuPyNumeric, it will fall back to NumPy. So here on this example, the numpy.linarc.tsq, I think it's list square, doesn't have any equivalent in CuPyNumeric. So when you try to run it, it will either tell you that it's falling back on NumPy, or if you don't have the warnings set properly, it may not tell you. So you may notice a decreased performance without knowing where it comes from. In my example here, I had the runtime warning, but it can be tricky, I think. And another thing maybe on the next slide that I have to specify is the best practices for CuPyNumeric are essentially the same as best practices for NumPy. So use output arguments to reduce memory allocation, use NumPy functions as much as possible. So this is all good practices that Jean-Marc presented last week. Use array-based operations instead of looping over the elements of your array. Use Boolean mask to avoid indexing. So this is all very straightforward, but there are also a few differences from NumPy that are documented in the CuPyNumeric documentation. In particular, you can have some weird behavior with indexing. So sometimes you can, this can be a bit tricky, but it's documented now, so it shouldn't be any problem. Okay, so maybe I'm going to give a short summary on QPy numeric of the limitations and the benefits that I found from this library. So the limitations I see is the fact that since there is this dynamic analysis of the code to distribute data, to determine the dependencies, etc., this generates a bit of overhead. This is supposed to be offset by pipelining the analysis with the calculations that are performed by the code. But for this to happen, you have to perform enough calculations. So this can be a limitation, but it's also quite standard in the GPU computing to perform a lot of calculations. It's what you should do. So for GPU, it's not a big problem. The main limitation that I found is that it's still in its beta phase, this QPy numeric library. So there are still some bugs. The documentation is not always up to date. I had some trouble running some examples last year. This year, I think it's better, but there are some something that are in the documentation that still don't work for me. And it's also not used very much for now in the Python community. So it's very hard to find some information about it, return of experience on it. But it's a promising project since it really aims at scaling your computation from CPU to multiple GPUs. Of course, a big limitation, but we are kind of getting used to it now, is that it's only it's made by NVIDIA, so it's only for NVIDIA GPUs, so you cannot use it on AMD GPUs. The benefits, on the other hand, I would say is very easy to install and to use. You basically don't have to change your code. It can run on CPU, GPUs, multi-node architectures. It can require maybe some refactoring if you want to use the GPU properly, because, for example, in my stencil example, well, it's very easy. You just run it, but then when I check the GPU use, I think my GPU was used like 20%, something like that. So it's not good. So I think you have, even if it's really easy to use, you still have to have the knowledge of your GPU and how you can use it the best way possible. I would say it's worth testing on your project to see if it works. And if it doesn't, you can still wait a few years so that it's in a better development phase. Or you can also use a different library, such as the other ones that we will present in this webinar. For the moment, I think the performances were not up to par with the other Python libraries for GPU, but we will test it more thoroughly in the Grayscale School this summer. So don't hesitate to join the Grayscale School to learn more about the performance of it. Thank you. And now I will give the floor to Jean-Marc, who is going to present another library, which is JAX.
Thanks, Alex. Now we are going to tell you about the JAX library. JAX is a Python library for NumPy-like array-oriented computing. JAX contains several sub-libraries and has an ecosystem geared toward deep learning. JAX is designed for high-performance computing and supports multiple hardware accelerator type without code modifications. JAX introduced a pseudo-language JAX expression to describe numeric function, making transformation easier. JAX is also designed for large-scale computation by managing several devices at once. So JAX coexists with NumPy, but it has its own array representations, the JAX array, with almost all the NumPy features. However, JAX array have a few special features. They are immutable. They are an instance of the JAX core tracer class, which play an important role in optimizing computation. They are associated with a device, and where NumPy use view, JAX use copies. The default type policy is different. Consequently, porting a NumPy program to JAX may be not straightforward. There are about 20 sub-libraries, including, of course, JAX NumPy. JAX CPy is present. It contains 10 of 14 CP sub-library. Not at all functions are present, but they may be present in a JAX extension, such as optimization with JAX out. Module related to calculation are JAX random, JAX image, JAX lax, JAX NN for neural network. You have module related to dev, like JAX debug, JAX profiler. Module related to hardware management, like JAX sharding or distributed. And module related to data representation with JAX tree, JAX typing, JAX DLpack. There are many device support with JAX, as well as all free priority system. Now we are going to talk about an important point of JAX, is transformation. A transformation is a function that transforms one function into another function. A typical example is JAX grad, which returns the application derived from if. The following functions are the main transformer to know. So JAX grad, JAX vmap automatically vectorize a function. JAX JIT, it's an on-fly compilation for the device just in time. The transformation can be combined, like JAX JIT of JAX grad of if. So JAX JIT is a key function to archive computing performance by adapting the code to the hardware, CPU, GPU, TPU. A transformer function generates its own bytecode called JAX expression, usable by other transformer functions, notably by JAX JIT. You can visualize it with a function make JAX expression. So here you have an example of JAX expression for the square function array, and example when you apply transformer JAX to the square function to have the derivation. So how does JAX work to compile the code? It begins by defining the JAX expression of the function to be compiled. Then the expression is optimized for calculation with the height level optimization, HLO. Finally, the code, a code specific to the device is written for CPU, GPU, TPU. The difficulty in using JAX lies in understanding the condition for using the JIT function. Without going into the detail of the exception, we can formulate the following three constraints. First, JIT compilation is possible only on pure function. A pure function has a whole input come from parameter, no access to the global variable, no access to static function variable. All outputs come from the function result. An internal change of a variable is not transmitted, and output array have a fixed shape. Second constraint is JAX compilation focus on array data, and you must indicate the other parameters as static. For example, with a reduction function, the value of axis. To do this, you can use the JIT function parameters, the static argument name, or static arguments to specify the static parameter of the function. At least JIT compilation optimize only JAX array and not the NumPy array. Now we will look at some examples of error written by JAX JIT. These examples are taken from the JAX documentation. Just-in-time JAX can be applied with a function called JAX JIT with a function, or you can use a decorator at JAX JIT to specify some argument with using JIT as a decorator. The common pattern is to use Python function functool partial to indicate the static parameter to JAX JIT. We will look at some example of error written by JAX JIT. This example are taken from the JAX documentation, the link under the title. Here the function returns a subset of input array where element is negative. As you can see, JAX return an error. Abstract tracer value encountered where concrete value is expected, etc. So in fact, the function is not a pure function. The size of the output depends of the data value. So you must processing data selection in JAX function or return two array data, one for the output and one for a mask data. A second example here, a function returns the mean element along axis parameters. So the messenger is abstract tracer value contained where concrete value is expected, axis argument to JAX array mean. So here the parameters axis is not an array and an array rise. So to call to read correctly this function, you can add a parameter static argument to define axis as parameters axis as a static parameters. The last example is a simple function return sinus of array. So here the messenger is very long, but at least you have a link to the documentation. And with this link, you realize you use a NumPy function instead JAX array function. So the recollection is just to replace NumPy by JAX NumPy. If you want to use GPU, you must create a JIT version of your function. Then you need to place your data in a GPU memory and just call your function with this data. JAX will automatically create a GPU version of your function. You can transfer data from CPU to GPU with device function, and you can also directly allocate memory on the device without temporary variable. JAX has its own profiler that can replace NVIDIA Inside. See JAX profiler module in documentation or profiling computation in JAX documentation also. And the output of the profiler, it's a JSON file. And to visualize the profiling, you can load the JSON file with the web editor Perfecto. And you have a snapshot of Perfecto with the list of streams created by JAX to run on GPU. Well, we'll finish the JAX presentation here. We will see more during Grey Scott School. In conclusion, you can say JAX is very comprehensive, powerful library, but getting started requires some work. JAX introduces concepts that are essential to users. The name of the documentation articles like how to think in JAX or JAX errors illustrate the effort required to use this library. Without this knowledge, the error messages are cryptic. Else, a library designed for computationally intensive algorithms, scaling between development and production are apparently easy. Its main advantage is that you can switch from one device to another simply by naming it. Furthermore, it supports a large number of devices, making the code highly mutable. We will now look at the QP library. So the goal project of the QP library is to provide a Python user with GPU accelerator capabilities without require extensive knowledge to the underlying GPU technology. The QP team is focused on providing comprehensive coverage of the NumPy and CPy API to become a complete drop-in replacement, as well as advanced data CUDA features to maximize the performance. So QP support NVIDIA hardware, of course, and also AMD GPU with experimental support. And for NVIDIA, the backend is QBlast, QRun, QSolver, QSparse, and so on. Here you have the speed up of GPU with a QP by type of calculation and data size. The results are better for large array. Indeed, the GPU is designed for massive data. And sample calculation like element by element operation. So you have a speed of 200 for element by element operation, only 2 for SVD decomposition for a small matrix. So QP has a very good coverage of the NumPy function. A table is available at this link. And also QPy provide CPy function with a table also available. Less well coverage by than NumPy. The memory management is very simple. The QP arrays are always stored in GPU memory. To copy CPU array to GPU array, it's simple creation of QPy array with parameter and NumPy array. And to copy GPU array to CPU, you use the get method of QPy array. To run specific code on the GPU, you need to define a function called kernel. There are 4 ways to define it. The kernel element with, it's an instance of the element with kernel class defined by a string with input types, output types, and formula code, and at least the kernel name. The raw type of kernel is reduction. It's an instance of reduction kernel class, also defined by a string. Reduction in array to scalar direction, for example, a norm, average, and so on. Another kind of kernel is raw. It's an instance of a raw kernel class. It's identical to the C CUDA kernel. So you write your C code in a Python string. And at least you have the kernel fusion with decorator at QP Faure, defining with Python syntax. Fusion because it supports element-wise and reduction at the same time. So an example of kernel fuse, it's the same definition as a traditional Python function. You can give an example of kernel with the Gray-Scott equation. So in this Gray-Scott equation, U and V are 2D array representing chemical concentration of 2 products. So updating the array U and V over time using the SPC color chains is done by QP kernel fuse below. And as you can see, the syntax is remarkably readable. Another example we will see during the Gray-Scott school, that the estimation of the Laplacian of U with finite difference can be obtained by convolving it with a stencil. Convolution of the 2D array is available in CP library, and QP provide a GPU version. So the calculation of the Laplacian on GPU can be in the right hand as follows. imports the function convol2D from QP CP signal and convert it with a stencil. And the convolution is performed on GPU. So we have all the elements to solve the equation on the GPU, the update by time step on U and V with kernel fuse, the calculation of Laplacian, and the transfer copy of data between GPU and CPU. Without going into the implementation details, we alternate between the computing and transfer. I name a copy phase to visualize the evolution of array U on CPU. So we have the following sequential diagram. So compute phase, after copy to CPU, compute phase, copy to CPU, compute phase, copy to CPU, and so on. Here is the profiling of the sequential Grayscott with inside NVIDIA profiler. You have two lines, the line kernel, it's in fact the GPU computing, and a line of memory dedicated to the data transfer. As you can see, the GPU is inactive for 25% of the time with this chance of Grayscott resolution. This highlights a common problem with GPU usage. Memory transfer time can be significant compared to the GPU computation time. With QPy, this problem cannot be solved by sticking with the GPU version of the NumPy and CP function. So we will look at two techniques that can improve processing time on the GPU. Both concern memory transfer. One technique involves using a memory type that allows faster transfer, and the other use concurrent computing to parallelize calculation and transfer. These techniques can be used on NVIDIA-specific CUDA function, accessible from the QP with low-level CUDA support library. So the first, it's a specific memory called Pine memory, also known as page lock memory, provide performance benefits to host device transfer, especially for large transfer. Pine memory allocation is done by alloc Pine memory function available in the CUDA module of QPy. So you define the size of the memory you want. You allocate it with alloc Pine memory, and after you create an NumPy buffer with this memory allocated. For the transfer, you must use a main copy function like a C version, defined in CUDA runtime. The direction of the transfer is defined by a specific keyword with a parameter of kind, copy device to host or main copy host to device. Now we'll talk about concurrent processing with QP. So parallel execution of different processing is possible with CUDA. It's a notion of stream, an equivalent of thread for CPU. Remember, thread has a different meaning in GPU domain. So we create a stream with CUDA stream function with parameter no blocking equal true. The processing associated to the stream is defined in a with statement and immediately run. If you define a second processing stream, both will run in parallel. To wait for the stream to finish processing, you must use the synchronize method of stream object. We will see now a technique to take advantage of the parallel programmation. It's called double buffering. The double buffering allows data processing and data transfer to occur simultaneously, and GPU is used at almost 100%. We define two streams, one stream compute and another one copy, and two buffer two out buffer A and B, and each stream works alternately on buffer A and B. So you start to compute and put the output in A. The second phase, two streams start. One stream to copy output A to CPU, and in the same time you compute and the output will done in buffer B. And as the next step, you switch A and B, and so on. We will apply this technique during the Gold School with QP. Our presentation of QP ends here. Let's move on to the conclusion. So we have very positive feedback of the library. No installation issue. The basic CPU, GPU memory placement mechanism are very easy to use. No surprise when using a GPU version of NumPy and CP function. The GPU kernel can be writing in Python syntax. The porting of the resolution of the Gold-Scott equation was very fast, and the speed gain for the naive adaptation is already significant, around 80. Access to a low-level CUDA function allow to use concurrency processing, and the documentation is good. So this is a mature library that allow you to easily port NumPy CP code to a GPU. Let's now briefly introduce the DPNP library. DPNP library is an Intel library for data parallel extension for NumPy. It's a drop-in replacement of core NumPy function. Almost all functions are available. You have a list available in the link. And also some CP functions are available. Not yet in a release major one. The latest version is 0.20. The backend of DPNP is Intel 1MPI. Use implementation of cycle for various architecture, CPU, GPU, FPGA. So DPNP is available for Intel GPU with Conda installation, and you have a specific build for NVIDIA AMD GPU. See cycle build documentation. It should also be noted that PyTorch is well suitable for using GPU outside of the deep learning project for which it was designed. PyTorch provides a simple and Pythonic API for GPU computing, easy transition from NumPy style code to GPU acceleration, automatically handling of GPU memory and device management, have high performance with optimized CUDA kernel, support vectorized operation and batching naturally, can enable, in some cases, asynchronous execution and overlap of between compute and transfer memory. And PyTorch reduces the development time comparing to low-level CUDA C++. Now I'm going to hand over to Alice for the rest of the presentation. Thanks.
Thank you, Jean-Marc. So we're going to conclude this webinar, but first I'm just going to comment the use of Numba for GPU, because we talked about Numba last week. So it's possible to use Numba on your GPU also, but for this you have to install a dedicated package, which is Numba CUDA. You have a dedicated documentation also. It's not on the Numba documentation. It's really Numba CUDA project. So it's for CUDA GPUs. The support for AMD GPUs is progressively disappearing. It used to have a support. If you look at the older documentation of Numba, there was a support for AMD GPUs, but now it's disappearing. So what's good with Numba CUDA is that it provides two abstractions that you can use in your code to use your CUDA GPU without having to write C code. So the first abstraction, which is really useful, is the vectorized decorator. So at vectorize that you can put above your function. And if you specify target equals CUDA, then it will compile your scalar Python function into a GPU universal function that will run element-wise across arrays. So the same principle as what NumPy does. It takes your function and vectorizes it for all the elements of your array. So here it's the same, but for the GPU. So it's quite useful. And also you can use another decorator in Numba CUDA, which is CUDA.jit, which you can see also a lot on Numba codes for GPU. So this will compile your Python code into a CUDA kernel this time. And you can also have the control over the thread blocks and the memory. So it's highly configurable. If you add the device equals true option, you can also define a device function that will run entirely on your GPU. So these are the abstractions that Numba CUDA provides you. I haven't tested them myself. It's made to be easy to use. However, the performance can be lower than other low-level libraries like PyCUDA, but maybe we will test it on our Grayscott code in the Grayscott school. We'll see. So yeah, that's just a few comments on Numba for GPU. But then let me give you a brief summary of the three main libraries that we saw in this webinar. So CuPy Numeric, JAX, and CuPy. So we made a quick recap here. So as CuPy Numeric is supposed to be the easiest to use, it can be also quite limited in its performance, and it is mostly interesting when you want to use multiple GPUs, when you want to scale your code to GPU with minimal effort. JAX, on the other hand, is much more complete. You can do a lot of things with JAX. It has high-level abstractions, and you can use it indifferently on CPU or GPU. But however, as Jean-Marc said, to port your NumPy code to a JAX code requires a bit of effort because you have to use JAX arrays and etc. So it can be a bit tricky at first. But then the porting to GPU is easier once you have a JAX code. And as for CuPy, it's a good intermediate because it is quite easy to use. It's not as complete as JAX, not as easy to use as CuPy Numeric, but it's really performant. It's also really robust because it's a very mature project. So yeah, it's a good intermediate to use. And so that leads us to our conclusion. So with the three libraries we presented, maybe you can see that they are all using the basis of vectorization that we have in NumPy, but they are applying it to GPU computing. So you write NumPy style code and then you execute it on the GPU by replacing NumPy as the backend. So CuPy Numeric, you do it via near identical API replacement. With JAX, you add some JIT compilation also on top of your JAX arrays. Yeah, so that was all for the Python for GPU webinar. If you want to learn more about the performance, compare all these technologies with the Grayscott code, don't hesitate to come to the Grayscott school in July. And thank you for listening, and we are here to answer your questions now.
Okay, thank you, Alice and Jean-Marc, for the nice presentation. We do have some questions. So, question from Alison: what is immutable? You cannot change it. Okay, so it's already answered. So, yeah, question from Gael: do you think CuPy Numeric could make CuPy deprecated?
I would say no. Honestly, I mean, I'm not sure they serve the same purpose exactly. The aim is to compute on GPU, but with CuPy Numeric, it's really to have the same code from the CPU to the GPU, which has some limitation because then it gives you first a false sense of security because you're like, okay, I just port it to my GPU and that's all. But then it doesn't properly work if you don't take care of the architecture. And for now, the Legate project, etc., they do a lot of the things implicitly, but not everything, I would say. Because, yeah, the use of the GPU by CuPy Numeric is sometimes less performant than with CuPy. Also, I think CuPy Numeric is quite new, maybe in 10 years, I don't know, maybe less, but for the moment, yeah, I would say it's not there yet. No, I don't think you can have one library that can replace all the others, because you have to take care of your GPU architecture at some point, I would say.
Okay. And also in Coupa, you have the support for AMD that obviously don't have in Coupa numerics.
Oh, yes. Yeah, I forgot that. Yes.
Question from Luca. Can you specify the type of GPU memory, global, shared, constant? I think it was for JAX, if I remember well. But of course, for the other, it's okay also. I'm pretty sure if you write an ugly string with your CUDA kernel inside and you try to compile it, you can specify if it's constant memory and stuff like this. But with a decorator, maybe, Jean-Marc, Alice?
I don't know. I haven't done it. Maybe. I don't know if Jean-Marc has some thoughts on it.
With JAX? I don't know.
Okay, so maybe it's not that easy.
The management memory, it's a large subject.
Oh yeah, question from Adrian. Will all these libraries trying to simplify use of GPUs? When would you need to develop custom CUDA code at all?
So I would say these libraries are for Python code, first of all. So as you see, there is not much CUDA code in these libraries. They are made to simplify it, but I think you still have PyCUDA in which you have to write some CUDA code, I guess. I would say when you want to have the best performance and your libraries are where you want to go deeper than what your libraries can allow you to do for the Python code, I would say. Maybe Jean-Marc, you have a different view?
No.
No, okay.
Or maybe if you want to specify the GPU memory you want to use. With the question of Luca. Question from Mathieu. In JAX, we want to use GPU. We do have to transfer array from the CPU and back to read the result, right?
Yes.
Or maybe an explicit transfer, yeah?
Yes, I think.
And also, I had a question about that. Can you implicitly transfer data just because JAX knows the device, and if you use you call kernel from the device and data on the host, transfer is automatic, or you have to specify it?
Certainly, we must specify it.
Okay.
I don't think there are implicit conversion. Maybe is not suitable. So if you want to do a transfer, it's explicit transfer.
Yeah, for big amount of data, it's always better. But sometimes automatic transfer for little pieces, it's nice. But okay. Question from Michel. Alice, could you tell us a bit more on Legate installation or point to another video where we can find the information, please? Someone interested in doing some magics with Legate.
So you can install Legate separately from Cupanumeric, but when you install Cupanumeric, I think it installs Legate. But if you want to install it separately, there is an NVIDIA Legate documentation. So I'm just going to put it in the chat. Yeah, and I think you just have to follow the process. I installed Cupanumeric with Legate, so I don't think I had to install Legate only. I had to a few years ago when Cupanumeric was not as well packaged as it is now, and it was a bit hard, but I think now it's easier.
And normally you will practice in the school.
Yes, we will install Cupanumeric in the school. If you want to install Legate without Cupanumeric, it's possible, but we are not going to do this, I think.
Okay, question from Guillaume. Is Cupa compatible with NVIDIA GPU Direct technology? So GPU Direct storage, GPU network, stuff like this?
I don't know precisely what is GPU Direct, but
maybe to specify for everyone. So GPU Direct technology. So you have GPU Direct storage. So this means that the GPU can directly read data from a disk, for example, NVMe stuff, and GPU Direct GPU network is to be to make sure the GPU can listen to a port directly without bothering the CPU with that. So GPU can access directly to the network and can access directly to a storage. and bunch of storage also now. So it's a magic done by Magnum.io, so under CUDA, low level. So it's NVIDIA only here, but maybe you can do this kind of stuff with CuPy.
I think it's possible, yes, because I use backend NVIDIA, and I remember the function we can load directly in a GPU the content of the file.
Yeah, so it's GPU direct storage. So that's it. So it's possible. Maybe not for the network, but at least for the storage, it's okay. Other question from Guillaume. Does CuPy support working with device buffers specified by address? So we guess you create your buffer and you pass it and you say, use this buffer, please.
I don't know. What can you do? It's an example of a pinode memory. So at the first step, you allocate memory. So you return a pointer of address, and after you define it to initialize an NP array. So in fact, the NP array is defined with an address. But this mechanism is CPU side. In GPU side, I don't know.
Okay, so maybe not yet. So Gail is happy, Luca is happy. Another question from Gail. Can DPNP works with TPUs? And if yes, which ones?
Device DPNP use device through a cycle. So if cycle is implemented for TPU, you can use TPU. I don't know the status of cycle portage for TPU in this project, but the link between DPNP and TPU is a cycle project.
I'm not sure if it's possible, but maybe it's ongoing. Okay, so Luca is happy again. Michel is happy. Oh yes, Guillaume, I just forgot. Yeah, GPU Direct, you have also GPU Direct RDMA, so you can get on a GPU, you can see the memory of another one. But maybe it's a bit too advanced for the previous question. But yeah, it's one of a part of these ones. But yeah, for the file, it's okay. For the rest, maybe it's a bit too advanced. So Guillaume, this is related to GPU Direct because generally in GPU Direct, would you need to pin device memory which you allocate in specific ways? So I was wondering if it was possible to handle this kind of memory. Thanks for your answer. Okay, so Guillaume is happy. So TPU or AI accelerator. Yeah, so Gail is happy. Jorge is happy. Okay, we are out of question here, but I can switch to mine for a couple of minutes if you want to get other question. So maybe a simple one. Once you use CuPy.CUDA, so you can use directly basically the C++ CUDA API, but in Python. Mm-hmm. But I guess that you are no more portable with AMD GPUs, or you have a trick under the hood that it makes that you can do it if you replace CUDA by AMD, I don't know, or CUDA by HIP maybe.
No, you lose the portability. Yeah.
Okay, so yeah, so if you want portability, do that in the very last test once you really know what GPU you want to use, and okay. Oh yeah, for JAX. So you mentioned it's deep learning, mostly oriented deep learning for computing. But if I want to compute with JAX, I'm pretty sure that there will be some autograd or stuff like this that potentially I don't want if I just want to compute just a Gray-Scott reaction. Can I disable it? Or maybe it's not enabled by default?
Why do you want to enable it if you don't use it?
Yeah, but maybe it's enabled by default, so I have to disable it. Or maybe it's not, and it's okay, but just to be sure.
No, if you don't use it's a great function, in fact, for JAX. If you don't use it, it's not a problem. There are nothing we are slow with this functionality if you don't use it.
But normally, once you want to compute derivatives, you need memory, and if you don't compute derivative but you allocate this memory, you lose at least memory, but also transfer, also lots of stuff. So, but maybe it's not by default, and there is no problem.
Right.
Would be really great if it's the case.
I think so.
Okay, nice. So we do have another question from Gail also. Do you know Python libraries compatible with AI accelerators like Colley in Kawe, NVIDIA Jetson Nano, of course the IPU, Habab HPU, AWS Trainium? We think they will replace GPU for HPC. Tough question.
Yeah.
I think the simple answer is nobody knows. Because
Yeah.
even the manufacturer do not know what will come, because they have a plan for 3 years and maybe 4, but not much. So nobody knows.
In fact, the solution of this problem is a cycle project to centralize APA to use accelerator for unique APA. If constructor participate to cycle, you can use it in a cycle project.
Yeah, mainly, yeah, you respond by the fact that you don't know by design. So you don't you are not stuck with one vendor. You can say, okay, I want really high level API, and then I use accelerator I want. And if in 10 years we have an amazing new accelerator on the market, we can use it because of the design, and we don't have to rewrite everything. And that's also a good point. Even if you know what you are doing and you say, okay, this is my computation, I know what I'm doing, do it again in a backend, even if it's yours. So if at some point you want to change, you want to update, you want to use what another colleague did, you can. You are not stuck with yourself. So it's always nice to have some design to prepare the future, because nobody knows for sure. Okay, so Gail is happy. Maybe yes, on profiling. So you cite Nsight, of course, if you want to profile with NVIDIA. Normally, you have a really nice support of Python since last year, and you also have NVTX. Do you have some NVTX in CuPy Numeric or JAX? Or maybe not JAX because it's not NVIDIA only, but CuPy Numeric, maybe you should have some NVTX at some point to not have the weird detail of what is a kernel which is launched, because it's a really complex name, but globally what you want to do in Python, or this function, and under the hood you have a lot of stuff. Now you should have this.
Yeah, I haven't tried it, but maybe I will check for the Grayscale School, yes, to profile a CuPy Numeric, our CuPy Numeric program, Grayscale program.
Yeah,
Okay,
normally should be nice.
Okay.
It's possible also with PyTorch if you use I don't remember which version of PyTorch, of course, but a recent one. You have NVTX also if you are used to Nsight. Of course, if you want to use other things, it's okay. But if you are used to Nsight, you have the support also now available.
Okay, good to know.
Oh yeah, question for JAX. So you mentioned you have a JAX device to know where is your array on host, on device, or whatever. But since there is now, it's experimental, but there is a NumPy device in ND arrays with a 2.5 beta version, if I remember well. Yeah. At some point, do you expect better compatibilities with JAX and NumPy, and you don't have to rewrite everything with JAX arrays, and you can use directly NumPy arrays, or maybe it's a bit too much? It's another open question, I'm sorry, but I do what I can.
The JAX array is a very important component of JAX. As I explained, it's an uncontainable interface to optimize, to compile to the right device. I don't think in the future you can replace JAX array by NumPy array, whatever the version.
Okay, so you still have to work a bit to be sure that you can work with JAX, even if you start with NumPy. Okay. Yeah, for CuPy numerics, do you have any news of the coverage of the NumPy functions? Because I remember that last year it was something like 70 or 80%. Is it better now, or?
I didn't check it here. I didn't check. I can check now.
Okay, should be better than last year, but how much I don't know. But
yeah, no, I don't know. But
normally
yeah, I'll include it in the Grey Scott course.
Yeah, normally 70%. You are really unlucky if you don't have the function you want.
Yeah.
Because basically all linear algebra stuff are covered. So if you manage to fit your problem into linear algebra, normally it's okay. Mm-hmm. Or you are really unlucky. And maybe on Legate also, once you use the Legate driver, it sounds very close to MPI run. Is it on purpose, or can you run MPI under the hood, or?
I don't know if it's on purpose.
Or maybe people are used to MPI and you do things like MPI and it's okay. And it's really powerful, so why not?
Yeah, I don't know. I haven't tried to use MPI under the hood. You can also run just with Python, but then you have to pass all the options by environment variables, so it's a bit harder. So I prefer to use the Legate driver. I don't know if it was made to resemble MPI. Sorry.
Okay, Youssef says, I look forward for the recording. So the recording will come soon, or maybe not, because there is a lot of day out in May, but will come normally as soon as possible. Or maybe yes, I'm pretty sure it's not possible, but why not? Can you use CUDA streams or an equivalent of CUDA stream with JAX to order your computing? Maybe OpenXLA do some wizardry under the hood for you? Or?
I don't think so. I never see that in documentation.
But it's the opposite with Legate. Legate will do all the wizardry possible to make sure that everything is parallel. So you will have streams, you will have everything on whatever device you want.
I look at the documentation. I see nothing about this.
Okay, there is still no question in the chat. So yeah, about Numba, you said, Alice, that the AMD support is progressively disappearing. Do you have an idea of the reason? Maybe they want to move to CuPy, and what is the possible reason for that?
I don't know. I know there is still a Numba for AMD project on GitHub, but I'm not sure it's. I think it's not official. I haven't tested it. No, I don't know the strategy of Numba. Maybe it's just following the CUDA supremacy. I don't know.
Or maybe on the AMD side, they have a new project coming, and maybe a kind of Legate or kind of CuPy numeric, and they want to use it and not the other one. I don't know. It's strange to drop support like this.
I mean, it was not official. I think it was experimental support. I'm not sure, but there was a full part of the AMD support in the Numba documentation that is now completely gone. but I'm not sure it was official. It was on the doc, maybe it was just experimental. It was from the version 0.5, I think, and we are version 0.8 of the Numba CUDA package.
Okay, so or maybe it's just difficult to maintain and
Yeah,
they
probably.
don't have the manpower for that. Maybe it's
Yeah.
as simple as that,
That was it.
unfortunately. Yeah.
Mm.
Or maybe for JAX. So you mentioned, Jean-Marc, that if you don't specify the type and you don't nicely say to JAX, okay, I'm using int or float or whatever, it will complain because the type is too generic. Can you use type int to help it, or it's not the way, not at all?
Type integer for JAX
The
array?
type int, the type int of Python, you know, for the once you write some Python, you can specify a hint for the
Yes.
type just
Yes.
for your development environment. But
Yes. In JAX array also you can do it.
Okay. So
Yes.
maybe JAX. So JAX can understand this type int, or
Yes, JAX array understand type int. Oui.
okay, nice, good point, good to know. I think I'm out of questions. But as Alice said during her presentation, of course you still need to have the knowledge of your GPU if you want to use a GPU well. So it's not magic. So it's nice to pass through one CPU to one GPU on the fly, but try to understand deeply what's going on your GPU, why you need to have this amount of data, why you need to do this or that transfer for this reason. Again, try to start as much thread as possible, otherwise you will kill your performance. So it's not magic. It's really nice to not have to be bothered by the transfer, by the allocation, by all this kind of stuff. But of course, you need to understand your GPU to be sure that you get the best performance possible. So since well, I'm out of questions, so let's close the session today. So thanks everyone for attending this webinar. As Mary said in the chat, don't forget to register for the Summer School if you want to get to attend to a satellite site, to ANSI, to online. Register. You will have a lot of material to study during the Summer School and after, if you want also. Thanks, Alice and Jean-Marc, for the nice webinar, the nice presentation, and all the wizardry with Python on GPU. So of course we will do more in detail in the school. That's the purpose of the school. That was just a really small teaser today with a lot of information, of course, because it's not a teaser, but it's a part of a teaser. So Gail is happy in the chat, so we have a lot of thanks. It's just that it's really definitely time to stop. So thanks everyone for attending this webinar. Next week it's a day out, so the next Thursday is a day out in France. So we cannot have Grace Code Thursday, so we meet 1 week after, so the 21st of May, to do some wizardry with Cocos. So the Cocos on GPU, the second part of the Cocos presentation of the Grace Code School. So Youssef is happy also, so everyone is happy. So thank you everyone. And yeah, see you on May 21st. Have a great weeks because and see you next time. Bye.
Bye.
Thank you. Goodbye.